All right, it is 8, so we'll get started for today. Um, like normal, for normal test days, we're going to do the first hour here in person, and then after that, the test will be open. You'll have until 11 to take it. But let's get going with our lecture for today. And if you remember from Wednesday, we have been talking about enzymes. So we looked at the basics of enzymes, how they bind their substrates. We looked at cofactors, looked at transition states. And then we ended on Wednesday with doing some math. And where we're going to pick up today is we're going to look at enzyme mechanisms. They're going to be similar to the mechanisms you went over in organic chemistry, except, they're for enzymes. So we're going to start with acid and base catalysis. Now, as always, like I've been saying, the examples we're looking in class, the reason we're looking at these is because they're well studied and they can be applied to a bunch of different enzymes. And so the first example of an enzyme mechanism is acid and base catalysis. And we're looking at taking a ketol group and making an enol group. And this can happen spontaneously. However, it is very slow because what you need to do is you need to take a hydrogen from this methyl group, or methane group rather, and add it onto this oxygen. And hydrogens on carbon are nonpolar, so they're very hard to remove. So there's two ways in which this reaction can be sped up. One is through the use of an acid, where this acid is donating this hydrogen. And one is using a base, where the base is actually pulling off the proton of this CH2. So there's two different ways in which we can speed up this ketol to enol reaction. And sometimes in enzymes, we'll see both acid and base catalysis. That's called concerted acid and base catalysis, where they happen at the same time. And when we're looking at acid and base reactions, usually the amino acids that are involved in this are asp, glu, his, cis, tyre, and lyse. Hopefully at this point in the semester, you can kind of picture these in your head a little bit, or at least after thinking about it and drawing it. So if you don't know what they quite look like, make sure you do go and review your amino acid structures. So let's look at an actual acid-base mechanism in a real enzyme. In the enzyme, we're going to look at is RNA ACE, or RNA ACE-A rather. And this is an enzyme that will break down any RNA that you eat. And the way it does that is through acid and base catalysis using histidine. So remember that histidine has a pKa of around 6. And what does that mean? Well, that means that at a pH of 6, you're 50% protonated and 50% unprotonated. So histidine, the hydrogen of histidine, is very easy to remove, and it's very easy to add another histidine or another hydrogen on the histidine. So in acid and base mechanisms, you're going to see histidine a lot. Now let's actually look at this mechanism in detail to see how the acid-base reaction is going on. So the carbon that is important for our first step of this reaction is 2'. And here, histidine 12 is going to take this hydrogen from 2' of RNA. So we have our our base histidine right here. So we're taking a hydrogen, and then histidine 119 is going to be acting like our acid. So we're going to donate a histidine to our phosphate backbone here. So what's happening is we're taking a hydrogen. This oxygen is going to attack this phosphate, right? And then we are giving a hydrogen to this oxygen right here. So in effect, we are cutting this bond and making a new bond. Remember, the goal of this is to cut RNA, and we already did that. We just cut RNA. And so one part of that RNA molecule is free to leave. That's the bottom part that we just cut. There's our new hydrogen. However, we're not done yet, because remember, for enzymes, for any catalyst, you always have to go back to your original starting conformation. That is, his 12 needs to be without a proton. His 119 needs to have a proton. After our first attack, his 12 has a proton and his 119 doesn't. So they're opposite. In addition, this RNA is cyclic now, and we don't want that to happen. We don't want this phosphate to be bound to 2' carbon. So we need to undo this cyclization reaction, and we need to switch the hydrogens around. So to do this, water comes in, and water is going to do a couple of things. One, the hydrogen of water, one hydrogen is going to be attached to his 119, and the OH is going to go and attack this phosphate. This will allow the 2' carbon to take back its histidine. And so you get your RNA back that's no longer cyclized, and your histidine 12 and 119 are back to normal, right? Unprotonated and protonated. And now you're ready to bring in another RNA molecule and do the same thing over again. So that's an actual acid and base reaction for a real enzyme in which we're cutting RNA. Our acid and base in this case are both histidine, just different histidine molecules. So any questions right off the bat about that, or any clarifications about this RNase A mechanism? All right. So here I have a couple questions, and let's see if people know the answers to this. I already answered one, so let's see if you remember what I said. In the RNase mechanism, we have histidine acting as an acid and a base. Why is histidine a great choice and a mechanism to act as both acid and a base? And the second question is, why can't RNase A cut DNA based on the mechanism we just saw? So who has answers for those questions? Feel free to pop it in chat when you have an answer. So first one, yeah, his has a pKa of 6.0, which means at pH 6, his is 50% protonated, unprotonated. Yeah, so histidine, you can easily add on a proton to histidine and remove a proton to histidine at the pH that the cell is normally at. So histidine is a great amino acid for acid-base catalysis. So yeah, that's correct. How about why can't we cut DNA with this enzyme? Why can we only cut RNA? If you're not sure, go back to that mechanism. Why is that mechanism specific for RNA only? Anyone have any ideas? Because this question isn't that hard. Does it have to do with DNA lacking OH on C2? Yes. Thank you for answering. I appreciate it. The first step in the mechanism is you need an OH, right? Like I said, this hydrogen is being taken off 2'. DNA just has an H there, deoxy. So like we said in this slide, when you're taking a hydrogen off a carbon, that's very hard to do. But taking a hydrogen off an oxygen, that's very easy to do. All right, so that's our acid-base mechanism there. Now, other things that are important for enzymes, metals. There's a lot of enzymes that use metal ions, and those are called metalloenzymes, as I have there. 1/3 of all enzymes are metallo, and they help by doing a couple of things. One, they can help orient the substrates properly so they can be in the reaction. So you learn from organic chemistry that for a reaction to happen, you have to attack from the right direction, right? The molecules have to be in the right direction for chemistry to happen, and the right orientation. That's what I was looking for. And so these metal ions help to orient molecules in the right orientation so we can have a reaction. They can also help in redox reactions because metal ions can change oxidation states easily. And so they can help perform these redox reactions. And they can also help stabilize negative charges. So any enzyme that usually works with like phosphates or DNA, they'll usually have magnesium ions because those magnesium ions can interact with the negatively charged phosphates and help that reaction go. One thing that you learned about in general chemistry that you probably forgot about is that metals can also make water more acidic. So metals can help polarize water and release that hydrogen. That's why if you ever go to a brewery, they're very careful about the amount of metals in their water, because the more metals they have in their water, the more acidic their water is, and that usually tastes makes bad tasting beer. So they have to be very careful about not only their pH, but the metal concentration. That's because metals make water more acidic. So let's take a step back from the nitty gritty here and just look at some big picture things. Why do enzymes speed up reactions? What do they do to speed up reactions? And we talked about, energetically speaking, they lower transition state energy. And transition state energy is what really is rate determining. But how do they lower that energy? So there are 4 different ways in which they lower energy. One, they have the proximity effect we just talked about for metal ions. They bring the substrates together and they point them in the right way. This speeds up a reaction, like I have there, about 5 times faster than non-catalyzed. And number 2 is kind of like the same idea. So they not only bind them, but they have them in the proper orientation. So proximity and orientation effects. 3, they have the charge groups that help stabilize transition states. And that's what we talked about on Wednesday when we were looking at transition states and how that's the most unfavorable part of the reaction. Enzymes help to lower that energy. But the biggest speed up by far is that they stop translational and rotation motions of substrates. So inside your cell, right, substrates, any molecule, they'll be moving left, right, up, down, back, forward in rotating. Molecules have 3D motion while rotating. And that makes proximity and orientation hard to achieve. It's hard for 2 molecules to just randomly hit each other inside the cell and a reaction happens spontaneously. But what an enzyme does is that they stop it from rotating, they stop it from spinning, and they bring them together. Now, this bringing molecules together, there is a penalty for that. Entropy. Right? It's very favorable for these molecules to be moving in all directions. It's very unfavorable to stop them and orient them in one direction. And so to pay this penalty, because binding a substrate, remember our equation, binding a substrate is spontaneous. Delta G is negative. However, there's an entropy penalty, so delta S is negative. Therefore, the reason why this is spontaneous is because of enthalpy. And we get this enthalpy from binding, right? Enzymes bind their substrates, and when they bind, they make new interactions. These interactions are enthalpically favorable, which makes the binding event itself favorable. So that's 4 different ways for enzymes to help speed up reactions. So any questions about how enzymes speed up reactions or anything up to this point? All right. And the last thing I want to talk about in the slide that from last week is that enzymes, although they're binding the substrate and that makes favorable interactions, what they really want to bind is the transition state. Because remember, we're lowering the energy of the transition state. And this is called transition state theory. And this image on the left really shows it off well. Imagine we have 2 different enzymes, enzyme 1 and enzyme 2. And they are doing the same reaction. They are trying to take a metal pole and break it in two, right? So our reaction is taking this metal pole and making two little poles, breaking it in half. So enzyme 1, and the way we do that is that our binding site has magnets around it, since these are metal. Enzyme 1 binding site is perfect for the substrate, right? It fits our substrate perfectly, and enzyme 2 can bind our substrate okay. However, enzyme 2, the binding site is better for the transition state. And enzyme 2 is going to be much faster than enzyme 1. And we can understand this looking at these energy diagrams, right? So we start at the same spot. The substrate has the same energy. And then our next area is the enzyme substrate complex. In enzyme 1, we're making a perfect fit to our substrate. So the energy of the enzyme substrate complex is negative. Remember, negative energy is good. That means that delta G double dagger is actually a bigger gap than it is in the uncatalyzed reaction. So if our binding site is perfect for our substrate, the enzyme is slower than non-enzyme reaction. Because we have just increased the value of delta G double dagger. However, in enzyme 2, you can see our binding site is perfectly fit for our transition state where we're half broke, half not broke. And so here, if you look at blue versus black, we are lowering delta G double dagger. So the enzyme is now faster than the non-enzymatic reaction. So basically what this slide says in a nutshell is that enzymes bind kind of poorly to the substrates, but bind really well to the transition state. And this binding to the transition state lowers delta G double dagger, which speeds up the reaction. So any questions about that idea? And this last bullet point here is, since we know this, since we know that enzymes want to bind the transition state, when you're making a drug or an antibiotic, you use what are called transition state analogs most of the time. These are compounds that look like the transition state because the enzyme will bind it. However, since they aren't the actual transition state, the reaction will stop right after there. So here, for example, we have a reaction, we're going L-proline to D-proline. Here's our transition state. The bottom are two analogs of the transition state, two molecules that look like the transition state. But what happens when this enzyme binds these analogs, the reaction will stop, the enzyme will be stuck, the enzyme will basically be dead at that point, and you have just inhibited a reaction. So that's how some antibiotics work. That's how some anti-cancer drugs work, by having a transition state analog. And question 9, we just went over that. So for the sake of time, I'm not going to answer that in class. So make sure you go back when you're studying for the final exam that you can answer this question. But with that, that's the end of our PowerPoint from Wednesday. Let me put up the one that I have for today. Up that right up. August 2nd. that. Yeah. And we're gonna just pick up with looking at some more catalyzed reactions. And the reaction we're going to look at to begin with is lysozyme. And we already talked about lysozyme. Does anyone remember from our discussion a few weeks ago? What does lysozyme do? Or what substrate does lysozyme work on? What does lysozyme cut? Gangliosides? No, they don't cut gangliosides. Destroys NAM, NAG, and peptidoglycan. That's exactly what it does. So lysozyme cuts the peptidoglycan layer, right? And it cuts the sugars in the peptidoglycan layer. And we're going to look at that mechanism. There we go. Easy for me to say right now. So for lysozyme to work, well, first off, if you remember from the peptidoglycan layer, it's made out of these NAG, NAM sugars, and they just repeat NAG, NAM, NAG, NAM, NAG, NAM, NAG, NAM. And lysozyme will bind to 6 of these sugars at a time. However, it only makes a cut between sugars D and E. And the way that this is going to work is that sugar D will always be NAM, sugar E will always be NAG. And that's because the binding site of lysozyme, the amino acids that are around there, will only bind 6 sugars and only bind when NAM is in position D and NAG is in position E. And you can see the mechanism we have going on right here, where we have our glycosidic bond, 1,4 glycosidic bond, and we just make a cut. Now, you might be wondering what's going on with 18O. This is showing that in this reaction, they use radioactive water, heavy water, to see where water would be added. So when they did this experiment in the presence of radioactive water. And then after the reaction was done, they determined, okay, where did my radioactive water add? They found, oh, okay, radioactive water is adding to sugar D. So we know where we're cutting. We're cutting between sugar D and sugar E. So what we're going to do is that first, we're going to look at the mechanism that lysozyme uses, but we're going to look at it non-enzymatically. And the reaction that is happening is that we're taking an acetal and making it a hemiacetal. And the intermediate for this is a carbocation. Now, you might have talked about this in organic chemistry. A carbocation is a positively charged carbon. So here we have our resonance structure where we either have a positively charged oxygen or a positively charged carbon. The structure on the right is more likely because oxygen does not want to be positively charged. So this is our transition state. Remember what we just talked about a few minutes ago. Enzymes really want to bind the transition state, right? That's their whole goal. So what I want you to be on the look for is I want you to kind of look at how lysozyme is stabilizing this carbocation, right? Because that's how we're going to speed up this reaction. And so here's the whole mechanism. And the two amino acids that are critical for this mechanism are GLU35 and S52, right? Now, before I start, hopefully, like I said, you know your amino acids by now. Looking at GLU35 and S52, what looks odd? Is there anything that looks odd? And there should be, because I already asked you what looks odd. What looks weird about those amino acids? They're bonded to carbon? No, they should be, right? They're amino acids. Amino acids are bonded to carbon. What type of amino acids are glutamic acid and aspartic acid? They're negative, okay. Then what's weird about those? Are they both negative? And the answer to that is no, they're not both negative, right? Glutamic acid 35 is neutral. There's no negative charge. So this mechanism already starts out a little weird. Glue is neutral already. It's not negative. Oops, did not mean to do that, Mark. But yeah. And the reason why it's actually neutral here is because you can change pKa's of amino acid by surrounding them with different molecules, right? I had you learn those pKa's. However, they aren't fixed numbers. pKa's change based on your local environment. If you're surrounded by a bunch of hydrophobic amino acids, your pKa will change. If you're surrounded by water, then your pKa is going to be like those numbers in the chart. So just something to keep in mind there. We start with glutamic acid 35 already being neutral. But let's look at this mechanism. So we have our NAGNAMs bind, and D and E here are the positions that we talked about. And the first step is that GLU35 is going to act like an acid, right? We're going to donate our hydrogen to this glycosidic bond. And right now, As52 is just hanging out. When we donate that hydrogen, sugar E is free to go. It's already been broken, and there's nothing binding this sugar to our binding pocket, so it is free to leave. And here is our transition state. Here's our oxonium ion, our carbocation, our positively charged carbon. And the way that this is stabilized is As52. We have a negative oxygen right next to this positive carbon, and we're actually going to make a covalent bond. This is called covalent catalysis. When you make a covalent bond between substrate and the enzyme, that is covalent catalysis. So we have our intermediate state here, where we have sugar D bound to our enzyme, which isn't great, because we need to release that sugar. And so what's going to happen is that water is going to come in. And by the way, since this is inside of a cell, water is used for mechanisms all the time. But water comes in, and the oxygen of water is going to attack the carbon of sugar D. Glue 35 needs to be protonated, so it's going to steal a hydrogen from that water. And as 52 can't be bound to D anymore. So during this, it's also going to break the bond between oxygen and carbon. And so sugar D is going to be released. It has that OH from the water molecule that came in. Glue 35 back to being protonated as 52 unprotonated. So very simple mechanism there between two amino acids. And that is how we can cut lysozyme or cut a peptidoglycan layer. And we're looking at acid and base catalysis. And we're also looking at covalent catalysis. So any questions about this mechanism? Any confusions? Any part where you got lost at? Anything at all? All right. So question one, I already answered. Glue 35 is surrounded by hydrophobic amino acids. Why is that critical? Because glue 35 needs to be protonated because it is donating a hydrogen. It's acting as an acid, so it needs to be protonated in this reaction. Question two, though, is something that I'll let you answer. So in the mechanism, we only looked at glue 35 and As52, not glue 3. Now, lysozyme has two residues, asp101 and arginine 114. And they're not involved in the mechanism, right? We didn't see asp101 or arg114 anywhere. However, if you mutate asp101 and arg114 to alanine, the overall shape of lysozyme doesn't change. Lysozyme still looks like lysozyme. However, doing this will slow down lysozyme by a lot. So I want to know what you're thinking. Why do you think if you mutate a residue that's far away from the active site, that doesn't change the structure, why do you think that would have an effect on enzyme speed? So this is one of those big critical thinking, the answer is not clear type of questions. So I want to know, what are your thoughts on this? Especially if you have not contributed it today, I would like to hear from you. Why do you think mutating something far away from the active site would have an effect on the speed of this reaction? switching to those other amino acids would change the charge in that location and change the overall pKa. That's actually a very good idea. And I like the way that you're thinking. It's probably not exactly that, because it probably won't change the pKa of Glu-35 just because they're so far away, and these are surrounded by hydrophobic. That Glu-35 probably won't change. However, you're on the right idea there. The reason why this, and this is actually something big when it comes to like enzymes, is that these have been refined over millions, hundreds of millions of years. These enzymes have been refined and mutated. And although an amino acid does not appear in the active site, it could be having a long range effect. So it is possible, for example, that this asp is interacting with another amino acid, which is interacting with another amino acid, which is interacting with Glu-35. And so if you mutate that asp away, you kind of break this chain. You break, and it is possible, you change Glu-35's pKa by doing that. And now Glu-35 is unprotonated. Or asp 101, arginine 114 could be interacting with amino acids that are interacting with the peptidoglycan itself. And if you break that interaction, you're affecting every interaction down the line. Now maybe you don't bind your substrate as tightly. So this question is really getting at making you realize, although we only talked about 2 amino acids, Glu and asp here, there are a lot more amino acids and enzymes that are making a difference in the speed of this reaction. And even amino acids that are far away from the binding site that you might think, looking at a protein, oh, this doesn't matter, this is so far away. It could still matter. It could still have a big effect on our protein there. So any questions about that idea or lysozyme in general? All right. Let's see where we have. Okay, so another mechanism we're going to look at is trypsin in the catalytic triad. So the class of proteins we're going to focus on are called serine proteases. And what a serine protease is, it's a class of enzymes. And they do a lot of different things, but in general, they break peptide bonds. And the amino acid that is critical for this is serine. Serine is going to be our reactive amino acid. However, there are also 2 other amino acids that are very important for this, asp and his. So here we have our 3 amino acids, serine, his, and asp. And together, they are called the catalytic triad. Just about all serine proteases have this catalytic triad mechanism. Even if these enzymes aren't related, that is, they evolved separately, they still have the serine this catalytic triad rather. And we're going to look at some examples of how this catalytic triad works in these enzymes. Now, for serine proteases, it can cut a lot of different proteins. However, certain serine proteases can only cut certain amino acids. And the type of amino acids they can cut are determined by what are called specificity pockets, right? So the three serine proteases we're looking at, chymotrypsin, trypsin, and elastase, they all cut different things. Chymotrypsin cuts bulky aromatics. That's how you spell bulky aromatics. Trypsin cuts ARG and lysine amino acids, and elastase cuts alanine, glycine, valine. And let's look at how their binding sites are made to accommodate these amino acids. So chymotrypsin cuts these big rings. Well, the specificity pocket has small amino acids. We have glycine on each side of our pocket, allowing this big molecule to come in. And then we just have serine down here to interact with our big bulky residue. So our specificity pocket is made out of these tiny amino acids. For trypsin, it's a similar idea where we have glycine on each side, but we have a negative amino acid here instead at position 189. This negative amino acid will bond with the positively charged amino acids. So that's why trypsin can cut after positively amino acids. Elastase, well, we don't have glycine here. We have these aliphatic molecules, so that small aliphatics, alanine, glycine, valine, can come and fit in this pocket perfectly. So you can see each pocket of these serine proteases have different amino acids to help bind different things. And if you notice, the only difference between chymotrypsin and trypsin is amino acid 189, because both glycines at 226 and 216 in both of these proteins. However, if you take chymotrypsin and you mutate this serine to aspartic acid, it does not become trypsin, right? You cannot cut positive amino acids if you make that change. And this goes back to the point that I was just making with lysozyme rather, is that for enzymes, amino acids that are far away from the binding site can still have an effect. Even if we cannot actually see how they interact, they can still have an effect on the mechanism and the reaction itself. So any questions about the specificity pocket? All right, so it's 8:50, and your test starts in 8 minutes. So anyone have any last minute questions they want to get off their chest before I sign off and let you at the test? How many questions are there? 492. Just kidding. I always like getting that question. Because to me, it doesn't matter how many questions there are, but I think there's like 45 or something like that. Or they're like 35 or 40. Somewhere between 35 and 45. I want to say that's right. Can I describe how ATP and calcium interact with troponin? I could. Can you? So basically what happens is that calcium binds troponin, and troponin releases, and tropomyosin then comes off the thin filament. That's basically it. Calcium binds. The binding of calcium is saying muscles need to expand and contract, so troponin falls off. Once troponin falls off, tropomyosin can follow, falling off, and then actin and myosin combined. Where does ATP come in? It doesn't in that interaction. ATP might come in like moving, actually doing the it could be that when the calcium binds, that allows the ATP to hydrolyze, but we didn't really talk about that, so I wouldn't really worry about that. All right. I'm not seeing anything else pop up. Just so that something else pops up. Does glucose have only one reducing end? Yes. Glucose would only have one reducing end. Starch? Depends what type of starch you're talking about. Are you talking about amylose or amylopectin, right? So no, starch does not have only one reducing end. Starch has many reducing ends. All right. Yeah, so I think we'll call it a day here. Give you a couple minutes to stress yourself out before the test starts. Go take a walk, take some deep breaths. Relax. You're going to do okay. Don't let that test anxiety get to you. If you have concerns during the test, like something happens, feel free to email me. Otherwise, good luck. And I will see you on Wednesday to discuss the test. And we're going to move into finals very soon here. So fun times. All right. Take care, everybody.